Hey everyone, so in the last lecture we saw the notion or the idea of Riemann. Okay, we saw the Riemann sum and everything. So question is how to solve examples. So today we are going to take examples. So one example will be with proper algorithm and we will see that it's an integrable function. Next I will take an example which is not integrable function. Then I will take an example on finite things like find upper sum if there are 10 partitions. If there is 10 nodes in a partition, then how to find upper sum, lower sum and arbitrary Riemann sum. And along with this I will tell you two nice theorems. Okay, one of the very basic and good theorems that Riemann proved. So all this I'm going to talk today. So let's go first with an example. So let me take f of x is equal to x square. And let me take the interval say 0, 1. Then I want to see what is integration 0 to 1 x square dx. Well, thanks to your syllabus in 12th, you know that answer is 1 by 3. But then let's try to obtain this answer using this Riemann sum. So what is the first thing you do? The first thing you do is you partition your domain. So let me call x0, which is my 0, x1, x2 and xn, which is my 1. But then what is this x1, x2 up to xn? This is not a nice partition if I want to solve a problem. So I should take a nice partition. So what I will do is I will divide my interval into n subintervals, each of equal length. In that scenario, you should always take this as b minus a upon n. That will be the length of the intervals. The nodes you will get. So in this case, it is 1 minus 0 upon n. So that means you divide into, so this is 0, this is 1 by n, 2 by n, 3 by n, n minus 1 by n, and this is n by n. And this you can say 0 by n. So you take this as the partition and that will help you to ease your calculation. So this is my 0, 1 by n, 2 by n, 3 by n, n minus 1 by n and n by n. So this is the partition and this is a nice partition because each of the subinterval is of equal length, which is 1 by n. This is of length 1 by n, 1 by n, 1 by n, 1 by n. The length is of 1 by n. Okay, now what you do? You find LPF. So what is my LFP or LFP? It is summation I goes from 1 to n, the minimum value of the function into the length of the subinterval. The length of the subinterval is nothing but 1 by n. So 0, 1 by n, 2 by n, 3 by n, n minus 1 by n, n by n. And what is the function x square? So it's a parabola. In the subinterval, look for the first subinterval. Function is an increasing function. You look for the point where function is taking the minimum value. So over this subinterval, this is the graph. So you can see that at 0, function is taking the minimum value. You go to the next subinterval, at which point function takes the minimum value. So this is the graph. As you can see, at 1 by n, function takes the minimum value. Go to the next subinterval. In that case, this is the graph. At which point function takes minimum value? At 2 by n, function takes the minimum value. Okay, so since it's an increasing function, you will observe that for increasing functions, your minimum value of the function will always be attained at the left end point because function is increasing, no? So the minimum value will always on the left side of the subinterval. Okay, so here what you get is, so let me write down first, let me split it first and then I will use this summation symbol. So f of 0 into length of the subinterval plus in this f of 1 by n into the length of the subinterval plus f of 2 by n into the length of the subinterval. At the end, minimum value will be at the left end point. So f of n minus 1 upon n into the length of the subinterval, which is 1 by n. And now if you want to write it in a much more nicer way, so okay, before that also the second step is you should put the value of the function. What is the function? X square. So what is f of 0? 0 only. So no need to write. What is f of 1 by n? It will be 1 by n square. So 1 by n square into 1 by n. What is this? 2 by n square into the length of the interval plus n minus 1 upon n square into 1 by n. Now you take out, what is this? If you observe, 1 square plus 2 square plus 3 square plus n minus 1 square whole divided by n cube, n cube, n cube, n cube. And now if you want, you can write in a nice way, which is nothing but summation divided by n cube, which is, that is common. Your numerator is changing, so index it with I square, and your I is going from 1 to n minus 1. So this is what my LFP is. Now let's try to further simplify it. Okay, so now what is sum? So I can take out 1 upon n cube outside because the summation is depending on I. So I can take out 1 upon n cube outside. What is left? Summation of I square. What is the sum of the squares of first n natural number? It is n into n plus 1 into 2n plus 1 by 6. So what is the sum of the squares of the first n minus 1 natural number? You replace your n by n minus 1, replace your n by n minus 1, and here also n by n minus 1. So 2n minus 2 plus 1, so 2n minus 1. So what I have is, I have LFP is equal to n minus 1 into n into 2n minus 1 upon 6n cube. This is what my LFP is. Okay, so that was only LFP. Okay, now you need to find UFP. What is my UFP? It is the maximum value of the function into the length of the subinterval. As we saw, everywhere the length is 1 by n. So let me take out 1 by n outside. For the first subinterval, so since this is the first example, let me show you properly. So this was 1x square, 0, 1 by n, 2 by n, and so on. So for the subinterval, at which point function will have maximum value? At 1 by n, because it's an increasing function. So at the right end point you will have the maximum value. Okay, so 1 by n you are having the maximum value. In this subinterval, at 2 by n you will have the maximum value. Similarly, at n by n you will have the maximum value. So in the first subinterval, at f of 1 by n you will have the maximum value into the length of the interval, which I took out outside. In the second subinterval, at 2 by n you will have the maximum value, plus at the end at n by n. So f of n by n into the length of the subinterval, which is 1 by n. So this is what my upper sum is. Now again the same thing, you put the value of the function. What is this? 1 by n square, because function is what? X goes to x square. Fine. So again here you have n square in the denominator, that will come outside. So you have 1 upon n cube, 1 square, 2 square, 3 square, n square. Summation I square, I goes from 1 to n. And what is sum of first squares of the sum of first n natural number? The first formula, n into n plus 1 into 2n plus 1 upon 6n cube. So that's what your upper and lower sum is. Now once you have upper and lower sum, what you do? You take the limiting case. Okay, so I don't want this now. So what is limit n going to infinity? LFP. This we have already studied. You take out n outside from here, n outside from here, so n cube will get cancelled. I have 1 minus 1 by n, 2 minus 1 by n upon 6, and here I have limit n going to infinity. What is this? This is 2 by 6, because this is 0, this is 0. Answer is 1 by 3. So the limiting case of LFP is 1 by 3. Same thing, you take limit n going to infinity of UFP. Take out n outside, take out n outside. So n cube will get cancelled. 1 plus 1 by n, 2 plus 1 by n. So 1 into 2. So again I have 2 by 6, which is 1 by 3. And as you can see, the limiting case of LFP is same as limiting case of UFP. Therefore the function is integrable. What was the function? F of x equal to x square. So therefore the function is integrable over the interval 0 to 1, and the integration value is 1 by 3. So that's how one has to solve a problem using Riemann sum. Okay, so yeah, so that was one thing. Now let me give you one homework problem by modifying the interval. So now what you do is you pause the video, or after the video also take this function over this interval, and you have to find what is integration 1 to 2 x square dx. Well, you know the answer is 7 by 3, x cube by 3, then upper limit minus lower limit, that is fine, but you do it using Riemann sum. Now when you do it by Riemann sum, the first thing is you need to partition the domain. Suppose it is starting from 0, 1, 2. So I am not interested in this part because interval is from 1 to 2. So what length you will take? So b minus a upon n. So length will be 1 by n. So here don't take 1 by n, 2 by n and so on. We are shifting it by 1 unit. So if this is 1, this will be 1 plus 1 by n, 1 plus 2 by n, 1 plus 3 by n. This is 1 plus n by n. Okay, so that's how your partition will be. This is nothing but your n by n. Usually people, what they do for f of x equal to x square over 0 to 1, they took 1 by n, 2 by n, 3 by n. Here also they keep on doing the same thing. But 1 by n will be closer to 0. I want after 1. So therefore, whatever partition you had, you simply shift it by 1 unit. So this is 1, then 1 plus 1 by n. Now over here, at this point, you will have minimum value. At f of 1 plus 1 by n, you will have the maximum value. In this subinterval, at 1 plus 1 by n, you will have the minimum value. So you take f of 1 plus 1 by n, and here f of 1 plus 2 by n. So like that, try to solve this problem and try to get the answer as 7 by 3. If you get stuck somewhere in the between, you can ask me in the comment section. Okay, cool. Now let's go for the example of a function which is not integrable. So I am taking the function over the interval 0, 1. So over the interval 0, 1, if the x is rational, then the output is 1. And if the x is irrational over the interval 0, 1, then I am taking the output 0. Okay. So what is the first thing? You partition the domain. You take the same partition 1 by n, each of length 1 by n. 0, 1 by n, 2 by n, 3 by n, n by n. Now what is the function? If it is a rational number, output is 1. For rational number, the output is 1. But between any two rational, there is again an irrational. So if there is irrational number, output is 0. 1, 0, 1, 0. Output is 1 if it is rational. Output is 0 if it is irrational. So again, between any two rational, there is irrational. Somewhere there is irrational, output is 0. Again, irrational, output is 0. Rational, output is 1. So this is what the function is. You can see the function is discontinuous at infinitely many points, and that's the key point. So we will see that this is not an integrable function. So we have the partition 0, 1 by n, 2 by n, so on. First thing is you find the lower sum. So you find LFP. In the first subinterval, look for the point where function is taking minimum value. A function is taking only two values, 1 and 0. What is minimum between them? 0. And will the function take 0 value? Yes, there is an irrational number over here. So therefore, the minimum value the function takes over this subinterval is 0. So 0 into length of the subinterval. Same thing. What is the minimum value your function will take over this subinterval? There are irrational numbers over here, and at irrational, function is taking the value 0. And what is minimum between 1 and 0? 0. So here also the function will take 0 as the minimum value. So similarly, in each subinterval, the minimum value your function will take is 0. So therefore, your LFP is 0. And when I take limit n going to infinity, what is limit of 0? 0. Constant limit is constant only. So my LFP comes out to be 0. Now let's try to find what is my LFP. Sorry, UFP. What is my UFP? In the first subinterval, look for the point where function is taking the maximum value. So the function is taking 1 and 0. What is the maximum value? 1. Does there exist a point where function is taking maximum value? Yes. At 0 it is taking 1. At 1 by n it is taking 1. So yes, there exists point where function is taking the maximum value. So over the first interval, maximum value is 1 into the length of the subinterval. Over here, what is the maximum value? 1 into the length of the subinterval. Again, 1 into the length of the subinterval. 1 into length of the subinterval. Denominator is common. What is numerator? 1 plus 1 plus 1 plus 1. How many times? N times. So n upon n, which is 1. So my UFP comes out to be 1. So when I take the limit, what is limit of n going to infinity UFP? It is limit n going to infinity of 1. What is limit of 1? It is 1. So as we see, the limiting case of LFP is not equal to the limiting case of UFP. It is 0 and 1. Therefore, this function is not an integrable function, Riemann integrable. Okay. And now once you have this function, you can give infinitely many functions. If someone asks you, can you give me 10,000 functions which are not integrable? Yes. First function is 1 0 over this interval. Take second function 2 0, 3 0, 4 0. Keep on changing the values. Take different values. In that way, you have infinitely many functions which are not Riemann integrable. Okay. So initially you don't know any single one, and now you know infinitely many functions. Okay, so that was about integrable and non-integrable functions. Before going to those examples, I forgot to tell you two nice theorems. So what are those two nice theorems that Riemann proved? He proved that if the function is a continuous function, if your f is a continuous function, then your f is always Riemann integrable. That means if you follow Riemann algorithm, your integration will always exist. Converse is not true. Okay, so for continuous functions, f is always Riemann integrable. For discontinuous function, it may or may not. We saw example where it was not Riemann integrable, and thus because of this theorem, I took an example of a discontinuous functions. So for discontinuous functions, it may or may not be Riemann integrable. Okay, but for continuous functions, integration always exists. So initially I took x square, which was continuous, and therefore we know. Because of that theorem, we know the integration exists, and we actually found the value of integration. Second important theorem is, if your function is Riemann integrable, then you take any partition. You take any partition P, and you take the limiting case of LFP. You take the limiting case of UFP, you take the limiting case of RFP. Now what is RFP? It is arbitrary Riemann sum. For LFP, you took those points where function was taking minimum value. Here you look for those points in the subinterval where function was taking maximum value. Here you take any point in the subinterval, and you take the value of the function. So look for the minimum, maximum, and take any point in the subinterval and take the value of the function and do the same procedure. Then you call it as a Riemann sum, arbitrary Riemann sum. Okay. So when the function is integrable, you take the limiting case of any of the three things, you always get the same answer. So I know that x square was continuous, so I know it's integrable. So therefore you can take any partition, and that's why I took the nicer partition 1 by n. So 1 by n, 2 by n, it was a nice partition, right? Each was having the same length, so I could take out the length outside, right? So I can do all those nice things if the function is integrable. And why x square was integrable? Because it was continuous. And whenever it is integrable, you can take any partition you want. So you always take the partition of equal length. Why so? Because your calculation becomes easier. Okay, so these are the two very nice theorems that Riemann proved. Okay, now let's go for the final example. So the function is x square plus 1. I am taking the simple function, so the calculations will be easier. Interval is 0 to 2. The question is, you have to divide this interval 0 to 2 into 4 sub-intervals and each of equal length. So what will be those intervals? So this is 2, this is 0, 1, 1 by 2 and 3 by 2. So now, so in the 4 sub-intervals, and all of are the equal length, which is 1 by 2. And I have to find LFP. So for LFP, I know I have to look for those points where function is taking minimum value. Here I have to look for those points where function is taking the maximum value. To find RFP, RFP means arbitrary Riemann sum. Then question is, which point I should take? Well, they have given that you have to take the midpoints. So to find RFP, you look for the midpoints. So you take the value of the function at the midpoints. Okay, so let me do one by one. So first find LFP. So for LFP, what you do, in the first subinterval, as it is increasing function, I told you the minimum value will always occur at the left end point. So x square, I know it is like this. So x square plus 1 will be like this. So 0, 2, 1, 1 by 2 and 3 by 2. So in this interval you can see at 0 it is taking the minimum value. So it is f of 0 into the length of the subinterval plus in the next subinterval f of 1 by 2 into the length of the subinterval plus f of 1 into length of the subinterval plus f of 3 by 2 into the length of the subinterval. So in each of the 4 subinterval, minimum value will be at the left end points. What is the second step? You put the value of the function. What is f of 0? 1. So 1 into 1 by 2 plus what is half? 1 by 4 plus 1, which is 5 by 4. 5 by 4 into half. What is f of 1? 2. 2 into half plus what is f of 3 by 2? It is 9 by 4 plus 1. So 13 by 4 into half. You sum it up. That's what the answer is for LFP. For UFP, what will you do? Okay, so your job is to tell me the answer for LFP. The second thing, you have to tell me what is UFP. Over this subinterval, you look for the point where function is taking maximum value. So it is f of 1 by 2 into length of the subinterval. Go for the next subinterval. It is f of 1 into length of the subinterval plus f of 3 by 2 into the length of the subinterval plus f of 2 into the length of the subinterval. So for UFP, what to do? You look for the points where function is taking the maximum value. So that is what your UFP is. So the second thing is you have to tell me the answer for this question as well. And the finally RFP. For RFP, what they have told, you have to take the midpoints. Okay, so for R arbitrary Riemann sum, f of what is the midpoint over here? 1 by 4. So value of the function at the midpoint into the length. What is the midpoint over here? So 1 by 2 plus 1 is 3 by 2. So and divided by 2 means 3 by 4. So f of 3 by 4 into length of subinterval plus again what is the midpoint over here? 1 plus 3 by 2. So it is 5 by 2. So 5 by 4 into 1 by 2. And what is the midpoint at the last? This plus this divided by 2. So 7 by 4. So 7 by 4 into 1 by 2. So what is f of 1 by 4? 1 by 16 plus 1 into 1 by 2. This is 9 by 16 plus 1 into 1 by 2. This is 25 by 16 plus 1 into 1 by 2. And this is 49 by 16 plus 1 into 1 by 2. And so that's what your RFP is. So when they talk about arbitrary Riemann sum, in that case they will tell you which point you need to take. So yeah, so that's the all kind of examples that one can expect or that one should know when doing Riemann integration. So your job is to tell me the answers of these questions, okay, in the comment section. And if you have any other doubt, you can ask me that as well. And if you understood, then do not forget to like, share and subscribe. Thank you.